Welcome back. In last lecture, we are in order of the element, and we have discussed some properties of order of element. So let us continue with some more properties of order of element and some results. So let us start with one result. So let me put that result in terms of preposition. Let G be a group and AB belongs to G. If first condition, order of A is equal to M, order of B is equal to N. Second thing, AB is equal to BA, and third thing, GCD of M and N means GCD of order of A and order of B is 1, means order of A and order of B are relatively prime, they are co-prime. Then order of AB is equal to order of A into order of B. So we have this result. So we'll prove this result. Okay, so if what is the meaning of this preposition? See, G is a group, any group, finite, infinite, abelian, non-abelian, there is no restriction on the group. Now we start with two elements. Now if order of A and order of B are M and N respectively, means both the elements are of finite order. So then order of A into B. So now you look at A into B. So A into B is also element of group. So we can talk about its order. So order of A into B is order of A and order of B. So this is not happened every time. In any group you take any two element, and if you want this thing, then this is not true in general. This is not true. This is true only if you have these three conditions. When both the elements are of finite order and these two elements A and B should be commute each other, the second condition. And third condition is what? The order of these two elements are relatively prime. There is no common factor between that two order other than 1. So in that case only order of AB equal to order of A into order of B. Okay, so if it is happened, then what we have? Order of the product. First we hear what we are considering product on the left hand side, then we are finding the order. Means order of the product is what? Product of the order. So order of the product is product of the order. This thing happened if I have these three conditions. So let us prove this result. So proof is very simple, and it is very important result also. So so given that, let me start proof from here. Proof. So let G be a group and AB belongs to G. Also let 1, 2 and 3 holds. So it is given. So now what I have? So therefore A raised to, okay, I want to prove order of AB is equal to order of A into B. So let order of AB is equal to T. I don't know what is the order of AB, so let me say it is T. So then what I have? Then see, order of A is M, so A raised to M. Order of B is N, so B raised to N. And order of AB is T, so AB raised to T. So these three things will be gives me what? Identity, because order of A is M, order of B is and order of AB is T, so its corresponding powers gives me identity. Now you look at AB raised to mn power. So what I have, it is A raised to mn into B raised to mn, because I have AB is equal to BA. If AB and B are AB, A and B are commute, then I can distribute this power to individual A and B both. We have seen this result before some lecture. So now I will write A raised to mn as A raised to m to the power n, and I will write B as B raised to n raised to m, and that I can do. But A raised to m is what? It is identity. So identity raised to n. B raised to n is what? It is identity. So identity raised to m. So it is identity into identity. It is identity. So what I get? AB to the power mn is identity. It means that order of AB will divides m into n. So it means what? Order of AB is what? Order of AB is T. So T will divides m into n. So let me say this is result number 1. Result number, say you may say it is star, because 1 I have already used here. So T will divides mn. So now if I prove mn divides T, then what I have? T equal to mn. If I prove mn divides T, so if you combine these two things, then it means what? So therefore T is equal to mn. And what is T? T is order of AB. And what is m? Order of A. What is n? Order of B. And we are done. So this is the idea. So our next next job is what? We have to prove that mn divides T. So how we prove this? Let us see. So let me start in this way. You start A raised to T into B raised to T, but that is what? I can write it is AB raised to T. Why? Because AB equal to BA. Let me give the reason, because AB is equal to BA. So I can write AB raised to T. Okay, but it gives me what? A raised to T into B raised to T is equal to AB raised to T. AB raised to T is identity also. So now you multiply both sides by B raised to T inverse. You multiply both sides by B raised to T inverse. So here I get only A raised to T, and B raised to minus T will be here. So now you take mth power on both the sides. So A raised to T raised to m is equal to B raised to minus T raised to m. So it gives me what? A raised to m to the power T is equal to B raised to minus mt. So it gives me what? A raised to m is what? A raised to m is identity. So identity raised to T is equal to B raised to minus mt. So it gives identity raised is equal to B raised to minus mt. So it gives me B raised to. So now again you take the inverse on both the sides. So what I get? E inverse mt is equal to E inverse, but E inverse is what? Identity. So it means what? B to the power mt gives me identity. It means order of B will divides mt. But what is order of order of B? Order of B is what? Order of B is n. So n will divides mt. But my m comma n, that is GCD of m and n is 1. There is nothing common between m and n divides mt. So it means what? N must divides t. So let us see what happened from here to here. See, if I have started A raised to T, B raised to T is equal to AB raised to T, and then after I raise the power m, A raised to T raised to m, and both the sides mth power. So if I consider here m power, then I get n divides T. instead of m I may consider n also. You look at a raised to t raised to n and b raised to minus t raised to n, then b raised to n raised to minus t and b raised to n gives me identity, and order of a will be m, so I here get m divides t. So similarly, so let me write similarly m will divides t. So what I get? So similarly this, so thus I have n divides t and m divides t, so it gives me what? And another thing is what? GCD of n and m is 1. So I have these three things: n divides t, m divides t, and there is nothing common between m and n other than 1 as a factor. So it gives me what? M n divides t. Product will also divides t. See, let me illustrate this thing by one example. See, suppose see, n divides t, it means what? It means what? T is equal to n into something, n into something. Let me say it is say s1 into s2 into say s3, and see m divides t also, so it means what? T can be written as m into some other, say L1 into L2 into L3 something, etc. Right. So it means what? Here m divides t, it means one of them, s1 s2 s3 will be what? M, because m is a factor of t, and here L1 L2 L3, so some L1 some Li is must be is equal to what? N. So it means what? M and n both appear in the factorization of t, so means t will be what? T will be somewhere m into n into something. So this mn will appear in the factorization of t, so mn will divides t. So I have, let me say this is double star, so from star and double star, so from star and double star we have t is equal to mn. So t is what? It is order of AB, and m is what? Order of A and order of B. So this is what we have, this result. Order of product is equal to product of order. And if you drop at least one condition among these three conditions, AB equal to BA, order of A and B are relatively prime, or first condition was what? Order of A and order of B are finite, then this result is not true. And you can find some examples in which at least one condition you drop, then you will not get order of AB is equal to order of A into order of B. So here commutativity is required, commutativity of A and B is required. Those two elements commute whose order can be order of A, B equal to order of A into order of B. So for that you need the commutativity of A and B. So that is one of the required condition. Okay, now let us consider some examples or some results. Which results gives you guarantee that your group is abelian. So in abstract algebra, those results which claims that the group is abelian, they are believed to be good results. Suppose if you have something this thing, then it is abelian. For abelian, what we have? Group is abelian if AB equal to BA for all AB belongs to G. But if I do not have this information, but I have some another information, then can I claim that AB equal to BA for all AB belongs to G? Then it will be a big thing. So let us consider this type of examples. So let me write instead of example, let me write it is a result. Let G be a group, then G is abelian if and only if AB square is equal to A square B square for all AB belongs to G. See, in previous some lectures we have discussed, you have AB raised to 1, then it is A raised to 1, B raised to 1. Means you can distribute one power to both the elements. Now AB raised to minus 1, then it is B raised to minus 1, A raised to minus 1. We have this property, right? Stokes' property. So this property says that you can distribute minus 1 power also, but not in this fashion. You have to distribute minus 1 power in the reverse order. If you have no any condition on group, yes, group is abelian, then you can distribute minus 1 power in, say if G is abelian, then we have this result, AB raised to n is equal to A raised to n, B raised to n. We have proved this result. And this n is what? It is for all n belongs to Z. You consider any integer, then you can distribute the n power to both the elements in the same order. But if G is not abelian, or you do not know whether G is abelian or not, then we have this situation. You can't distribute n power individually in left to right or right to left. But for minus 1 power we have this freedom. Suppose I have AB raised to minus 2, then it is not like B raised to minus 2 or A raised to minus 2. I can't write this. Yes, if G is abelian, then it is fine. But if G is not abelian, or A and B are not commute to each other, then I can't write this. I have information about these two only, 1 power and minus 1 power, not for other powers. Yes, of course 0 power, that is obviously AB raised to 0 is what? It is A raised to 0, B raised to 0, that is fine. So I have information about only these three things, because it is identity and this is also identity. But here what I have, this result says that if G is abelian, then you can distribute 2 power individually. So that is what, this is a particular case of this result. So this way is very trivial. Okay, but this way is also correct, and that way what it says, AB square is equal to A square B square, means if you can distribute 2 power to both A and B from left to right, then your group will be what? Abelian. So you get the condition of abelian in terms of the distribution of the power. So let us prove this result. Proof is very simple. So let us let G be a group. Let G be a group, and let us prove this way. Let G be abelian. Suppose G is abelian. Suppose G is abelian. Now we want to prove this thing. AB square is equal to A square B square for all AB belongs to G. So let AB belongs to G. Now AB square is equal to what? I can write it is AB distributivity. So it is what? A times BA B. So this is what? Associativity. So A times AB B, because G is abelian. I can write BA is what? AB. So again you use the associativity, so it is a square b square and we are done. So this way is very clear. Now conversely assume that ab square is equal to a square b square for all ab belongs to G. Okay, so now what we want to prove? What is our claim? So our claim is G is abelian. G is abelian. Okay, so for that what we have to prove? We have to prove xy is equal to yx for all xy belongs to G. Okay, so you take xy belongs to G, any two elements of group. So by assumption, what I have assumed, ab square is equal to a square b square for any ab belongs to G. So I have xy in G, so xy square will be what? X square y square. So it means what? This xy square I can write it is xy into xy, and this x square y square can be written as xx yy. So this is what? Let me use the associativity. So it is yx and this side is y. You keep y and x together, so it gives me x, xy and y. So now from left side you can cancel x, from right side you can cancel y, because we are in group, so cancellation law holds. So it is what? Yx is equal to xy, because by cancellation law, by cancellation laws. Okay, so what we have proved? For any xy in G, yx is equal to xy, so therefore G is abelian, and that's it. So this proves me group is abelian. So now let us prove one more result. Let G be a group if such that ab raised to n is equal to a raised to n b raised to n for 3 consecutive integers, then G is abelian. So what this result says, suppose G is any group and AB raised to n equal to A raised to n, B raised to n, means you can distribute n power to both the elements from left to right as in the same order. Then okay, this power n can be distributed, but for what? For 3 consecutive integers. Consecutive means one after another. For 3 consecutive integers, then G is what? Abelian. See, for example, suppose I have this ab raised to 5 is equal to a raised to 5, b raised to 5. ab raised to 6 is equal to a raised to 6, b raised to 6, and ab raised to 7 is equal to a raised to 7, b raised to 7. Means 5, 6, 7, 3 consecutive integers. and I am able to distribute 5 power to both A and B in left to right power order. So, and if I have this thing for all AB belongs to G, then I can claim that G is abelian. G is abelian, and it is true for any integer, any integers, but that 3 integer must be what? Consecutive. See, if in place of, suppose if I consider say 9, 10, 11, then what should I have here? 9 power. Here it should be 10 power, and here it should be 11 power. Then G is what? Abelian. So for any 3 consecutive integer, if I have this situation, then I can claim that G is abelian. So let us prove this result. So proof. So let G be a group such that AB raised to n is equal to A raised to n, B raised to n, AB raised to n plus 1 is equal to A raised to n plus 1 into B raised to n plus 1, and AB raised to n plus 2 is equal to group, and let n be any integer. Such that, so I have considered what? G is a group and n be any integer such that this happened. A raised to n plus 2 into B raised to n plus 2. Say this is the result number 1, 2 and 3. So for 3 consecutive integer n, then next integer is n plus 1, and the next integer is n plus 2, and n is any integer, and this is true for such that this for all AB belongs to G. So now my claim is what? G is abelian. Okay, so to prove this G is abelian, let me start with 1 and 2. So from 2, let me start. AB raised to n plus 1 is equal to A raised to n plus 1 into B raised to n plus 1. But this can be written as AB raised to okay, fine, let me write in this way. Okay, it's okay in this way. A raised to n plus 1 into B raised to n plus 1 is equal to AB raised to n plus 1. So I can split this is A raised to n into A, and this is what? B raised to B raised to n into B. N plus 1 can be split as n and 1, n plus 1, n and 1, and here I can write it is AB raised to n into AB. But this is what? A raised to n into A into B raised to n into B is equal to AB raised to n is what? A raised to n into B raised to n into A into B. So this is by 1. So by left cancellation law, A raised to n, that can I cancel, and from right side I have B, so I can this cancel. So therefore what I have, AB raised to n is equal to B raised to n into A. So I hope this is clear. So let me say 1, 2, 3, then let me say this is result number 4. Okay, so what this 4 says, A will commute with B raised to n. A B raised to n or B raised to n A, both the things are equal. So ultimately what we get, if I started with 2 and using 1, I have started 2 and I used 1, then I get this result. So from this 2, what I get? AB raised to n, B raised to n A. So you can look in this way, here n and n plus 1, so I have nth power, n and n plus 1, then smaller one. So similarly, if I use these two things, that is second and third, so similarly me write little bit. Similarly, from 2 and 3 we get ab raised to n plus 1 is equal to b raised to n plus 1 into a. So result number 5. Okay, so now from 5 let me start ab raised to n plus 1. So from 5 ab raised to n plus 1 is equal to what? It is b raised to n plus 1 into a. So therefore what I can write, a into b raised to n into b. I can split in this way, and this is what b raised to n into b into a. N plus 1 can be split in this way. So therefore now ab raised to n is b raised to n a. So this is what b raised to n into a into b is equal to b raised to n into b into a. So this is by 4. So by 4 a and b raised to n can commute. So in place of a b raised to n I can write b raised to n a. Now what I have, b raised to n on left side. So by left cancellation law what I have, I left with a into b is equal to b into a. So because by cancellation law. So what I have proved, you take any two element ab, then ab is equal to ba, and to prove this I use all these three conditions. So thus G is abelian. So this result says what? If you have any integer and for corresponding to that integer you look at the three consecutive integers, and if you distribute that three consecutive integers power to individual to every element, then your group will be abelian. So now let us see one more result. Let G be a group such that AB cube is equal to a cube b cube, and ab raised to 4 is equal to 5 b raised to 5 for all ab belongs to G, then G is abelian. Some people also prove like this. So what this result says? See, you compare this result with previous two results. Since first we proved if AB square is equal to A square B square implies G is abelian. Then we proved AB raised to n is equal to A raised to n into B raised to n, AB raised to n plus 1 etc. implies G is abelian. Right? And in this result we claim that if AB raised to n plus 1, AB raised to 3 equal to A cube B cube, and AB raised to 5 is equal to A raised to 4, sorry, A raised to 5 B raised to 5 implies G is abelian. So to prove this, what we can do? So with the help of these two things, given things, either you prove AB square equal to A square B square, then using that result we claim that G is abelian. The another way is what? Using these two things, you prove that AB raised to 4 equal to A raised to 4 B raised to 4. Then what we have? We have 3, 4 and 5 consecutive powers which can be distribute. So using this result we can claim that G is abelian. And the third way is what? Third way is you just manipulate something and you prove that AB is equal to BA for all AB belongs to G. So let us try to prove this result. So here we have these three ways. So let us prove what we can do here. So proof. Let G be a group let AB belongs to G. You take any two element in G such that AB cube is equal to A cube into B cube. So result number 1, and AB raised to 5 is equal to A raised to 5 B raised to 5. Result number 2. Okay, so now let us see what happened. So now if we prove that AB equal to BA, then we are done, because A and B are any two elements. So now from 1, see, AB cube is equal to A cube B cube. So it gives me what? AB, AB and AB. I can write AB cube means AB, AB, AB 3 times. And here A cube means what? It is A and it is B, B, B. So if I club these elements in this way, you keep A this side and you keep BA and BA and B. Then here I have A, B, B and this B. So it gives me what? A cancel, B cancel by cancellation laws. So it is what? BA into BA, that is BA square is equal to S square B square. This is S square, this is B square, and that thing BA is BA square. So what I have proved here, if here I have BA square, then I can distribute this 2 power in reverse order, S square B square. So that is a nice information. Let me say it is 3. Result number 3. See, if AB cube is equal to A cube B cube means if I can distribute 3 power in left to right, then I can distribute 2 power in reverse order. So that is the meaning of this result. Okay, so again by 2, what can I do? So again from 2, what I have? AB raised to 5, it will be what? A raised to 5, B raised to 5. You give the same argument, so it will be what? AB 5 times, right? It is AB 5 times is equal to A into, let me write in short way, A raised to 4 into this is B raised to 4 into B. So you make this pair like this A, and now you keep this BA together, this BA, then BA and then BA. So it is what? BA raised to 4 into B is equal to A into A raised to 4 B raised to 4 into B. So A cancel, B cancel. So what I have? It is BA raised to 4 is equal to A raised to 4 B raised to 4. So again we have, if you can distribute 5 power from left to right, then you can distribute 4 power from right to left. So that is also another information. So let me say it is result number 4. Okay, so now what we have? So now let us start from so now from 4, what I have? BA raised to 4 is equal to A raised to 4 into B raised to 4. So BA raised to 4 can be written as BA square into BA square, and this is what? A raised to 4 into B raised to 4. So BA square is what? S square B square. So I can write here A square B square, and BA square is again a square b square. So it is a square, a raised to 4 is a square into a square b square into b square. So here I am using, so this is by what? By result number 3. So here I can cancel a square cancel and b square will be cancel by cancellation law. So I left with, it is b square a square is equal to a square, b square a square is equal to a square b square. Okay, so now what? But I can write b square, fine, let me write b square a square as it is, b square a square as it is, but a square b square is what? ba square, it is ba square. So this is by, again by 3. So it gives me what? Now b square a square is what? It is b a and ba square is what? It is ba. So here b is on left and a is on right. So by cancellation law I have ba is equal to ab and we are done. So what we have proved, for any ab belongs to G, ba equal to ab, and for that I used these two things. So what I did here, I just manipulate something, and I frequently use the associativity and the laws of indices and cancellation law. So with the help of these three things, and that we can do in the group, we can prove AB equal to BA if I have these two things. So if a 3 power and 5 powers can distribute individually, then group will be also abelian for 3 consecutive integer or 2 power or 3 and 5 power. So then we can claim that group is abelian. So in the last three results we are discussing that when our group is abelian. So all these 3 results gives me a guarantee that in this situation your group will be abelian. So that is that believed to be a big thing in group theory, that we get information from somewhere that my group is abelian. Okay, now let us see one more. Next result, let G be a group if A square is equal to identity for all A belongs to G, then G is abelian. This is also very nice result. See, you start with a group and suppose you have this information that every element square is identity. You take any element of the group and its square is identity, then your group must be abelian. So let us prove this result. So let G be a group. Let G be a group such that A square is equal to identity for all A belongs to G. See, once A square is identity, it means what? It is A into A is identity. So you multiply both sides by A inverse. So here A inverse into A is identity. So I left with A, and here A inverse into identity. So this. So it means what? It is true for all A belongs to G. Means A square is identity. It means that the inverse of that element is itself. Element and its inverse will be same. And if you have A and A inverse are equal, then also you have S square is equal to identity, so you can go in back direction also. Okay, but I have this information, so let me say this thing is result number 1. S square is equal to identity for all A belongs to G. It is equivalent to what? Element and its inverse are same. So means we are dealing in a group in which every element is self invertible, means inverse of every element is itself. Then group must be what? It is abelian. So to prove abelian, what I have to prove? I have to prove that xy is equal to yx for all xy belongs to G. So let xy belongs to G, and I will prove that x into y is equal to y into x. So xy belongs to G. So therefore what I have, let me start with this xy square. So what will be xy square? So xy square will be identity. Okay, let me write in this way. Xy belongs to G, it means what? X into y is also in group, because its product is also in group. But for every element in the group, I have its square is identity. So what I have? This xy square is what? It is identity. So it means what? It means what? Xy square is identity. And I want to write, fine, it is what? Xy square is identity. So xy inverse is same as xy. I can write in this way. Xy inverse is xy, because xy square is a square is identity, then a is equal to a inverse. So xy inverse is xy. But I know that I can distribute this minus power in reverse order by Stokes' property. So it is xy. Y inverse x, y inverse x inverse is equal to xy. But again, element and inverse are also same. So y inverse is y and x inverse is what? X. So is equal to xy. So this is again by 1. So in this way, what I have proved, for any xy in G, yx is equal to xy. So therefore G is abelian. So therefore G is abelian. Yes, so this is a nice argument. Let me recall this argument once again. You have started any two element from G, then its product is also in G. But for any element of the group, I have this information, its square is identity. But its square is identity, it means what? That element, that is xy, is self-invertible. So we have xy inverse is xy. Now but I can distribute minus 1 power from the reverse side, so that is y inverse x inverse. But again, in our group, every element is self-invertible, so y inverse is y and x inverse is x. So we have yx is equal to xy. So now let us give one more result. If G is a group of even order, if G is a group of even order, then there exists at least one element. Then there exists at least one element A which is not identity, such that such that A is equal to A inverse, means self invertible element. You consider any group of even order, then you must have at least one element other than identity whose inverse is itself. Yes, in any group, inverse of identity is always identity. But you will get element other than identity that is also self invertible. That is a big thing, and you will always find in any group of even order. See, so then logic is very simple. So let us give the proof. So I have to start with a group and whose order is even. So let G be a group of order 2n. So 2n, n is some positive integer. So 2n is always even. So that is order of G is what it is, 2n. So order of G is 2n. Okay. So then we can write G is what? G is one element is identity. Let me that element is denoted by E. Then next element is A1, A2, A3 and so on up to A2n minus 1. This 2n minus 1 elements and this is one element. So all together gives me 2n elements. So among these 2n elements, E is identity and these are non-identity elements. So I hope this is clear. So now I will construct a set. Now for each AI not equal to E, you consider a set for each AI we have AI inverse belongs to G. You consider any element of this form, then its inverse is also again in G, because in group every element has inverse. Now you consider this set. Consider a set A is equal to what? Say you consider AI belongs to G. You take one element from G, A1, A2, A3 or like that. Consider a set AI belongs to G such that its inverse, AI inverse is equal to AI, and this AI is not equal to identity. Consider a set, let me write in this way. Consider a set AI is not equal to AI inverse, then you list these two elements AI and AI inverse, comma. This is not a product, it is just comma. See what we are doing. You take A1. Suppose A1 and A1 inverse are different, then you write here A1 and A1 inverse. If A2 and A2 are inverse are different, then you write A2 and A2 inverse. If A3 and A3 inverse are equal, then you will not write here A3 and A3 inverse. So like that. So those you are collecting those element and its inverse which are different. Okay. So here corresponding to every element you have one pair. Right, once you have one element whose inverse is different from that element, then you have here you are listing two elements. So then what I have, then number of elements in A is even. First thing, because at a time we are adding two elements, so number of elements in A will be what? Even, and this E will be not be in A. Identity element will be not in A because identity inverse and identity are equal. So when two elements element and its inverse are equal, then that element is not here. We are collecting those elements whose inverse are different. So identity will not be here, and the number of elements in A is always even. So now you see, here we have in group 2n elements, and A is a subset of, also A is a subset of G. All these elements in A are coming from the G. In G I have total 2n elements. Identity is not here. So whatever the elements in A will be coming from only this many elements, and these many elements are what? 2n minus 1, that is odd number of elements, and here I have even number of elements, total number of elements are even. So thus the maximum number of elements in A are 2n minus 2. Here 2n minus 1, you add one by one, and suppose A contains maximum number of elements, then here I have 2n minus 1 elements. So these are in numbers odd, and I have to dump here only even number of elements. So there must the maximum number of elements which can be allowed in A is what? 2n minus 2, one less than that this number of elements. So 2n minus 2. So it means what? There is one element you will find from among these elements which is not here. So thus there exists A belongs to G such that among this element, means it will be other than identity, such that A is not equal to E and this A is not in A. This A will not be in A. So A is not in A. It means what? Why A is not here? Because its inverse will be not be different. Implies A and A inverse will not be equal. Sorry, it must be equal. If A and suppose if A is equal, A and A inverse are different, then A must be in A. But A is not in A, it means what? A and A inverse must be equal. So what I have proved? So I have proved that you must get one element in group which is different from identity and its inverse is itself, means it is a self-invertible element. Means in other words you can say its a square is identity, A square is identity. So what is the meaning of this result? Let me explain by one example. See, this result says that if order of G is equal to 8, then what I have information, then first information, identity inverse is identity, that is fine. It happens in any group, it may be finite, infinite, abelian, non-abelian, whose power is odd, order of the group is odd or order of the group is even, whatever the group is given, identity inverse is identity, that is fine. But this result says me that, second thing says that there exists A belongs to G, A is not equal to identity such that A inverse is equal to A. Among these 8 elements, forget about identity, so we left with 7 elements. Among these 7 elements, one element is there whose inverse is itself. So that is the meaning of this result. And this is what we have discussed its proof, but we can see this proof in this way also, just for understanding. And what I am right now giving, it is not a proof is already there. But say let order of G is equal to 8, then G can be written as what? Identity A1, A2, A3, A4, A5, A6 and A7. 7 plus 1, 8. Now identity inverse is identity. Identity inverse is what? Itself, identity. So now you forget about this. Now A1 must have inverse, because we are working in group, so A1 must have some inverse. So there are two possibility. A1 inverse is first one. A1 inverse is A1, and second possibility is A1 inverse is not equal to A1. See, if A1 inverse is equal to A1, then we are done. We get one element A1 which is other than identity, whose inverse is itself. We are done. So I assume that A1 inverse is not A1. So A1 inverse is what? It is definitely among this one, among this A2, A3, A4 up to A7, must be from somewhere. So without loss of generality, I assume that A1 inverse is what? A7. Suppose A1 inverse is A7. Now similarly, A2 inverse is also somewhere. There are two cases. A2 inverse is itself, or A2 inverse is some other. Suppose A2 inverse is itself, then we are done. We have one element other than identity whose inverse is itself. So without loss of generality, I assume that A2 inverse is not A2, so it is say A6. So let me make a pair in this way without loss of generality. Now A3 inverse is what? Either it is itself, then we are done. Suppose it is not itself, then it must be what? It is A5. Say A5. Then what about A4? So A4 inverse must exist and it must be in the group. Now A4 inverse cannot be A1, A2 or A3 or A5, A6, A7, because they are already engaged to each other. So A4 inverse must be itself, and hence what we have? A4 is element in group which is other than identity and its inverse is itself. So in this way, so it is a simple logic. If you have 2n elements, then you remove identity, then you left with 2n plus 1 element and try to make a pair, then you left that pair, and pair is what? Pair is of element and its inverse, different inverse. Then you must left with at least one element whose inverse is itself. So that's what this result want to say. Okay, so now we stop our this lecture here, and in next lecture we will discuss some more problems, or we may go into the concept of subgroup. So we stop this lecture here, and in next lecture we will introduce the notion of subgroup. So thank you.